Bismillahirrahmanirrahim. Assalamu alaikum and hello to everyone. This is Maria Khan from mymathsclub.com, and here in this video we are going to evaluate a very important limit, that when limit of this sequence function 1 plus 1 upon n whole power n, I just forgot to write power n here. So when the limit of this function when n tends to infinity converges towards Euler number, we need to prove it, that why and how it is getting converged towards Euler number. We know that Euler number is an irrational number and its value starts like 2.71818 and so on. So this behavior is being observed through all positive integral values, means for all natural numbers. So in order to evaluate, in order to understand this important limit, we are going to take the help of a very important theorem here. And this theorem states that when a monotonic increasing sequence, which is bounded above, it is going to be convergent towards a supremum or upper bound. And when a monotonic decreasing sequence, which is bounded below, it is going to be convergent towards its infimum, that is your lower bound. So we're going to take the help of this theorem here, and we first going to prove that this function is either monotonic increasing or decreasing. Once it is done, then we are going to prove it whether it is bounded below or above, and after that we are going to understand its convergent value, so where it is going to converge. So let's get started. So over here we are going to take the help of our binomial theorem, okay, and we are well aware of the binomial theorem, and when our power n is a positive value or a natural number, then the formula of the binomial theorem after expansion is going to look something like this. You can see it here. So I'm just trying to expand it, just writing the formula for acquaintance. And I'll keep on moving till the last term bn. And remember that whatever the power you're having over here on this binomial expression, you just increase one value to this power, so total n plus 1 number of terms you're going to get once you expand this binomial expression, okay? So that's what you get. So if you're having power n here, you're going to have n plus 1 terms after expansion. So this is it. Now we are going to use this formula here, and for our 1 plus 1 upon n whole power n, here 1 is behaving as a and 1 upon n is behaving as b here, okay? And now we are going to substitute these values in our binomial theorem, and let's see what we are going to get here. Excuse me. So this is going to be 1 power n plus n, this is my a, and minus 1, b is 1 upon n. That's how you keep on moving on. N times n minus 1 upon 2 factorial, 1 power n minus 2, 1 upon n square, whole square, plus n times n minus 1, n minus 2 upon 3 factorial, 1 power n minus 3, 1 upon n whole power cube. And you keep on moving on and on and on till you write b of n, and b is 1 upon n whole power n. That's what we are going to write at the end. And as we are writing the last term, you see the last term is having n factorial values in the numerator as well as in the denominator. So it's definitely going to be cancelled, and simply b of n is left finally, or 1 upon n whole power n is left. So this is it. This is your a n minus n. Okay, so it becomes 1 power 0, and 1 power 0 is 1. No matter what base you're using, whenever you have power 0, the answer is 1. So you know that well. So now we're going to write a simplified form. So this n and this n will get cancelled, and we know that no matter what power you're having on your 1, the result is always 1. Okay, so 1 power n is 1, so you simply write 1 here, and 1 power n minus 1 is also 1, so you simply write 1, and the second term as well, and that's how you keep on moving. N times n minus 1 upon 2 factorial is going to be expanded, and it's 2 times 1 power 1, 1 upon n square, because 1 square is 1, so that's why we simply write 1. And this denominator n square is going to cancel this n, so now simply n is going to left in this denominator. So keep this thing in mind. And you expand your 3 factorial as well. It's 3 times 2 times 1. N power n minus 3 is 1, 1 upon n cubed, and that's how you move on. And finally, the last term is 1 power n is 1 upon n power n. That's what you're going to write. And as I told you before, this whole thing, n factorial upon n factorial, is going to be cancelled. So simply you are having 1 here, and 1 power n minus 1 is 1 power 0, I repeat. So the result is always 1. So 1 into 1 is 1. So what is left only is your 1 upon n whole power n. That's it. There you go. Now we come to the next step. And now it's 1 plus 1 plus. Now what we do, we are simply having this n left in the denominator, so we just write n minus 1 upon n times let me just write these values in an organized form. So it is now 1 upon 2 times 1, and then n minus 1 upon n. That's how I move on. I simply write my numbers first. So 1 upon 1 dot 2 dot 3, it's actually multiplication dots. So now this is the rooster in my neighborhood. So n minus 1 upon n, and this n minus 1 upon n. Simply having n square we were having, so we just adjust it like this, up plus 1 upon n power n, like that. Now you see you're having n minus 1 upon n here, so it's gonna divide both these terms separately. That's what we are going to do. So it's gonna look, n upon n is 1, we just write 1 minus 1 upon n. That's how we are just applying a kind of backward substitution here. Okay, so we keep on moving on. 1 minus 1 upon n times 1 minus 2 upon n plus, keep on going, plus 1 upon n power n. Now we come to the next step here. So this is my binomial expansion. What I'm having here, I'm having sum of all these terms. So this is a kind of series. It is a series indeed. So, and it is involving n plus 1 terms, the sum of n plus 1 terms, right? So this is comparatively 1 plus 1 upon n whole power n is representing a series of terms of n plus 1 terms. So I can represent this stuff as s of n, Sn, like that. So S is representing series. So Sn is equals to 1 plus 1 upon n whole power n. Yeah. So that's what it is. Now I need to make it clear what kind of sequence is this? It is a sequence of different series, right? So what kind of, whether it is an increasing sequence or decreasing sequence, that's what I need to find out. So I need to see what is the nature of the next consecutive series. Either it is less than S of Sn, or either it is greater than Sn, right? So what I do at the place wherever I'm having my n, I'm going to replace it by n plus 1, and then I'll try to understand whether the new sum is going to be greater than this old sum or not, okay, or whether it is less than it. So that's what I need to find out. So I'm going to do what? There is no need to apply binomial theorem once again. What you do, you're having this series already over here, so you just replace your n by n plus 1. Wherever you're having your n, replace it by n plus 1, and then try to understand each and every term, whether it is greater than the previous corresponding term, or whether it is less than the previous corresponding term. Okay, so it's like that. So let's try to write down here s of n plus 1, how it looks like. So okay, so Sn plus 1 equals to 1 plus 1 plus 1 upon 1 into 2 times 1 upon 1 minus 1 upon n plus 1 plus 1 upon 1 into 2 into 3, 1 minus 1 upon n plus 1 times 1 minus 2 upon n plus 1. And that's how I keep on moving till I get my last term, that is 1 upon 1 plus n plus 1 whole power n plus 1. So that's it. Now I need to see what? You see, first two terms are similar, means 1 plus 1, and s of n was also having 1 plus 1. I need to focus on from the third term, and you see this expansion is having n plus 2 terms, okay, because the power on that binomial expansion was n plus 1. So the number of terms is one value greater than the power, so you know that. So we are having n plus 2 terms here. So now let's try to compare from the third term, all right, and this is going to help us understand whether s of n plus 1 is greater than Sn or less than Sn. So let's see it. If I talk about my third term here, for that purpose, definitely in order to understand, I need a number value, a numerical value, so I just say that n is equals to 3 here. So now 1 minus 1 upon n, I'm just picking the Sn term, the third term of Sn. It is giving me this answer. Okay, it's gonna give me 1 minus 0.33 is giving me 0.666 and so on. Okay, it's a recurring decimal number. Similarly, the corresponding 1 minus 1 upon n plus 1, it is giving me 1 minus 1 upon 4. 3 plus 1 is 4. So it's 1 minus 0.25, that is 0.75. Yeah, so this value is greater than the previous one, right? So this thing shows that 1 minus 1 upon n is less than 1 minus 1 upon n plus 1. Or it is greater than this 1 minus 1 upon n plus 1 is greater than 1 minus 1 upon n, right? Now in the same manner, you see the fourth term, okay? That is 1 minus 2 upon n plus 1 is greater than 1 minus 2 upon n. You see, if we are just generalizing the terms now, okay? So you see all the terms of your Sn series, it is greater than the terms of all the terms of your Sn plus 1 is greater than Sn terms. Now the last term we are just trying to compare of Sn, 1 upon n power n is this, 1 upon 3 cubed. And it is giving me this value, 1 upon 27 is 0.037. So this is it. And similarly, 1 upon n plus 1, power n plus 1. So this is 1 upon 64, and definitely it is gonna give you values smaller. So this is a little contradiction, but you see this, the very last term. The last term is not going to put much impact on the entire sum. Okay, so keep this thing in mind. That's the only difference we are having, unlike other terms. Okay, so now no need to get confused in this. I told you that the last term is extremely small, so it's not going to put much impact on the entire sum. Okay, so let me just write down here, it's not going to put any much strong impact on the sum. So that's it. Now we move on here, and as all the terms starting from the third term, all the terms of your Sn is less than the terms of your Sn plus 1, so the sum of your Sn plus 1 is entirely is the lump sum, or the net sum is giving you that will be greater than your Sn. Do we just write down here? Okay, so, and we have to specify this, that for all n greater than or equals to 3, the sum of n plus 1 is greater than Sn. Okay, so S of n plus 1 terms is greater than Sn terms. Okay, it's like that. So this thing shows that Sn is monotonic increasing sequence. All right, so every next consecutive series is going to be greater than the previous one. Okay, so this is an increasing sequence. So once this is an increasing sequence, so the next steps is to show that it is going to be bounded above. So that's what we need to show now. Okay, so the first step is done. It is now proven that it is an monotonic increasing sequence. Now we need to show the boundedness. Okay, so we need to show that now it is bounded above. So what we do, we are going to write the expansion once again, like that. And then we see that this series, or this result, is less than 1 plus, now we are just using logics here, okay? It's a real analysis, it's a logical approach. It is 1 plus 1 plus 1 upon 1 into 2 plus 1 upon 1 into 2 into 3 plus, and so on up to 1 upon n factorial. Why this is so, why I am doing this, we need to understand this first. So let's try to understand this thing by comparing the terms. Okay, so again we are using n equals to 3 in order to understand this concept. All right, remember, whenever we multiply any number with a proper fraction, the result is going to be decreased. Okay, so here when I use 3 here, I'm having 2, 1 minus 1 upon 3, that is giving me 1 upon 2 times 2 upon 3, and is giving me 1 upon 3, that is 0.3333, and so on. This is the result. And you see this answer is definitely less than 1 upon 1.2, means 1 upon 2, that is 0.5, right? That's it. Similarly, 1 upon 1.2 dot 3, that's what I'm going to pick up next. Into 1 minus 1 upon n, 1 minus 2 upon n. Let's substitute the value n equals to 3 here, get the result. 1 upon 6. Let's try to simplify. 1 upon 6, 2 by 3, and 1 by 3. It is giving me actually, it's not 1 upon 9, I'm sorry, it's 1 upon 27. So that's what I'm getting here. So it's 1 upon 27 actually. You can make a rectification, which is still lesser than 1 upon 9. And 1 upon 1.2.3 is 1 upon 6, which is definitely, this value is greater than the previous value. Okay. So see this term, 1 upon 1.2.3, which is 1 upon 3 factorial, it is greater than the above term that we have just solved. Okay. That's actually 1 upon 27, and I just showed 1 upon 9. So this is it. You see, all these terms are coming out to be less than simply the reciprocal of the factorials. Okay. So that's the reason why I just write like this, that the sum of this previous series, for some of these terms of the previous series that I have just written, it is less than this new adjustment. Okay. And I'm going to further write that this new adjustment is less than and before doing that, let me just try to compare my last term as well. 1 upon n power n is giving me this answer when I substitute n value 3 there, and 1 upon n factorial is 1 upon 3 factorial, that is 1 upon 6, and it is greater, you can see. But the last terms are also being, they have just been compared as well. So you see, all these terms are coming out to be less than these new terms. So the sum is also definitely going to be less. So this is it. Okay. So now we are going to make, apply one more logic here, that this new adjustment is going to be further less than, let me just rub this first. It's going to be further less than one plus 1 upon 2 power 1. Okay. That's not 2 square, I'm sorry, 2 power 1 here. And this fourth term, at this place I'm going to write 1 upon 2 square. Okay. So you see, the first 3 terms of the second step and the third step, they are same. So we have to make comparison from the fourth term. Okay. It's like that. Up to 1 upon 2 power n. It's not n, it's actually n minus 1, 2 power n minus 1. We need to compare why it is less. Okay, so you see 1 upon 1.2.3, that is 1 upon 6. Okay, it is equals to 0.1666, and 1 upon 2 square is 1 upon 4, that is 0.25. So you see 1 upon 2 square is greater than 1 upon 6. That's why we say. And this behavior is maintained till the last term. Okay. And if I talk about the last term, 1 upon n factorial. Okay, 1 upon n factorial is 1 upon 3 factorial, that is 1 upon 6. That's, we have just written before, 0.1666. And 1 upon 2 power n minus 1. It's not it's not 1 upon 2n, it's n minus 1. Wait a second, let me. So 1 upon 2 power n minus 1 is giving you the same result, okay? So 1 upon n factorial is less than 1 upon 2 power n minus 1. So now you see we are going to understand the behavior of this series, that is actually a geometric series. You can see it's a geometric sum of the geometric progression, sum of the terms of a geometric progression, because you're having a common ratio half here. The first term is a, so we are going to use the formula of the geometric series, and it's going to be written like this, and I'm going to write the general form right after this. So it is a times 1 minus r power n upon 1 minus r. So here r is my half, it's a common ratio, okay? So I'm following here the general formula, which is this general formula of the geometric series, that is, sorry, it's a times 1 minus r power 1, r power n. So let me just write here. Let me just remove this. Okay, a bracket 1 minus r power n, yeah, upon 1 minus r. That's it. That's the formula that I'm using here. All right. So now, once when I solve this denominator, 1 minus half, it is giving me half. Okay. So I'm going to divide the numerator terms individually by this denominator. It is 1 upon half minus half power n upon half. Okay, so 1 upon half is 2, so we can write 1 plus 2 plus, you see you're having same base here, they're getting divided, so you can shift the denominator power above with the negative, with the opposite sign. So it is giving you an appearance something like this. You see some kind of value is getting subtracted from 3, so of course this result is less than 3. Okay, it's like that. So this thing shows that it is actually bounded above. This sequence Sn, this series, I must say, it is increasing as well as bounded above. That's why it is going to be converged towards a number that is between 2 and 3. Okay, and the best selection over here is nothing but an Euler number, because Euler number is arithmetically it is proven here. You can see that once when I use my calculator and try to substitute the value of n and keep it increasing drastically, like at the first place I just use n value 10 here, okay, and I will see my result. It is giving me this 2.59, and it is I'm going to drastically increase it and make it 100. It is now giving me 2.7048, and I just make it 1000. You see, I'm just trying to make, I'm just giving a huge jumps here just to see the Euler number. It is, we are now getting closer and closer to Euler number. So see, once when you drastically increase your n is approaching towards infinity, the sequence is getting closer and closer to the Euler number, okay? And you see Euler number is between 2 and 3, you know that well. And it is, while proving the boundedness, we have also understood, and it is now very well, it's quite clear that the number to which this sequence Sn is convergent, it is an Euler number, it is between 2 and 3. So thus we just assert that the limit of this sequence, which is actually a series, when n approaches to infinity, is converging towards an Euler number. And this is basically, I just again forgot to write my power n here, so this is it. So that's how we just try to understand this useful theorem. And we first proved the the increasing sequence nature, and then we proved the boundedness, and that's how we just understand its convergent behavior. And then we try to understand the limit point. So that's what the best way we can understand it through real analysis. I hope you found this video helpful.